Welcome to lecture number 11. In the last 3 lectures I discussed in detail 2 examples of interesting global stable homotopy types. These were 2 different global refinements of the non-equivariant stable homotopy type known as MO, the unoriented Bordism or tone spectrum. One of these global refinements, the one that I denoted by little m, capital O, is globally connective, and it is closely related to geometric Bordism of equivariant manifolds. The other global refinement that I denote by a capital M, capital O, comes with tone isomorphisms for equivariant vector bundles, so it's globally oriented, and it's related to the theory of global formal group laws. Today I want to explain some more theory. So we have already introduced the global stable homotopy category. Let me remind you what the definition was. So my notation is mathcal GH, and it is the localization of the one category of orthogonal spectra at the class of global equivalences. So this is a perfectly fine definition, modulo the fact that you have to show existence of such a localization or maybe smallness of the localized category. But if this were all we had available, then I wouldn't be able to tell you much about it. For this definition to be workable, we need a little bit of extra structure. Without any additional structure, for example, I wouldn't know how to show that this category has a triangulated structure and that it becomes a compactly generated tensor symmetric monoidal category. The same kind of issue persists if we approach this from an infinity categorical perspective. We can certainly define a quasi-categorical localization by starting with the one category of orthogonal spectra and localizing at the class of global equivalences in the quasi-categorical sense. But without any additional tools, I wouldn't be able to show that this is a presentable symmetric monoidal stable infinity category. And this is definitely things that we want to know. Today I want to discuss an extra piece of structure, namely the global stable model category. And this extra structure is very instrumental in exactly solving those issues, and it will allow us to prove these things about the homotopy category or about the quasi-category that underlies the global stable homotopy category. In this lecture, I will assume familiarity with the language of model categories. Also, the establishment of the global stable model structure is relatively long and involves several steps that are fairly routine and that I consider as relatively boring. So I will not dwell on these routine steps and rather concentrate on those aspects that are specific to our situation, to the global stable homotopy theory, and where we can learn something about global equivalences of orthogonal spectra. The remaining details are all written up, and you can read about them in section 4.3 of the Global Homotopy Theory book. The strategy to establish the global stable model structure follows a well-established pattern of which there are already several examples in the literature. The standard procedure for constructing stable model structures on categories of spectra can roughly be broken up into 5 steps. In the first step, one establishes a level model structure, which is sometimes called a strict model structure, or in our context we'll call it a strong model structure. After all, spectra consist of some sequence of spaces, or there are functors on some indexing category, and you can lift a model structure on spaces or on equivariant spaces, pointwise or objectwise. In the second step, one gets a better grip on the class of cofibrations. Of course, these are characterized as the morphisms that have the left lifting property with respect to acyclic fibrations, but there's often a more explicit characterization in terms of a latching map. The latching map roughly records how the stuff below some fixed dimension maps to the stuff in the particular dimension, and you want this map to be a nice closed embedding or an equivariant cofibration of some sort. In the third step, you have to make an educated guess about the kind of omega spectra that should come up in the particular context. So this would be the non-equivariant omega spectra or equivariant omega spectra, or in our context, there'll be global omega spectra. You then have to characterize the omega spectrum condition in terms of some locality, so you have to find suitable morphisms such that when you map out of them, this detects omega spectra. The fourth step is usually the one where the mathematical content happens. You have to take the morphisms from the previous step that detect the omega spectrum condition, and you have to show that they belong to the class of equivalences presently under consideration. So for example, pi star isomorphisms or equivariant pi star isomorphisms, or in our situation, global equivalences. The final step is to perform a Bousfield localization using Quillen's small object argument. For example, the fibrant objects will be produced by running the small object argument with respect to the class that on the one hand contains the acyclic cofibrations of the level model structure, and to this you add the morphisms that detect the omega spectrum condition, suitably modified so that they are cofibrations as well. The standard procedure for constructing stable model structures on categories of spectra has been established in a bunch of papers that serve as a blueprint for what we're going to do here. The first example is the paper by Bousfield and Friedlander, where they consider sequential spectra and they construct a strict and a stable model structure. Incidentally, in this paper there's another example of what we're doing, namely the category of gamma spaces, where Bousfield and Friedlander also run the program. For symmetric spectra, Hovey, Shipley and Smith have established strict or level-wise and stable model structures in their celebrated paper. Mandel, May, Schwede and Shipley run the program for a whole class of so-called diagram spectra, and these include in particular orthogonal spectra, where the non-equivariant stable model structure is established. For equivariant orthogonal spectra, the stable model structures are established in the three papers that I'd already mentioned in one of the first lectures: the paper by Mandel and May, the thesis of Martin Stolz, and the celebrated Annals paper by Hill, Hopkins and Ravenel on the covariant 1 problem. All three papers use the same weak equivalences, namely those morphisms that induce isomorphisms of equivariant homotopy groups for the group under consideration and all its closed subgroups, but they differ in the cofibrations that are being considered. In all three cases, certain latching maps have to be equivariant cofibrations, G times OM equivariant cofibrations, but there's different isotropy conditions away from the image of that map. I will now guide you through this procedure in our situation with the aim of establishing the global stable model structure on orthogonal spectra. The first step is a level model structure. And in our situation, I call this the strong level model structure on orthogonal spectra. I have to introduce the weak equivalences and the fibrations in this model structure. So here is the relevant definition. So a morphism f from x to y of orthogonal spectra is a strong level equivalence or a strong level fibration if and only if for all n greater or equal to 0 the based continuous OM map, OM equivariant map, that I get by evaluating this morphism at r to the m with its standard inner product. So f r to the m from x r to the m to y r to the m is an OM weak equivalence. In the first case, for the strong level equivalences, or an OM fibration, if we're talking about strong level fibrations. So maybe I should remind you what a OM weak equivalence is. This just means that for every closed subgroup of OM of the orthogonal group, when we restrict to the fixed points under the action of this closed subgroup, we get a non-equivalent weak equivalences of fixed point spaces. And OM fibration is the same with Serre fibrations, so on the fixed points for every closed subgroup of O of M, we get a Serre fibration of topological spaces. There is an equivalent and slightly more invariant way to look at the strong level fibrations and strong level equivalences. So equivalently, the same F as above. F is a strong level equivalence or strong level fibration. If for all compact Lie groups G, and all G representations V, the map I get by evaluating at V and then taking G fixed points, so F of V G fixed points, on X of V G fixed points to Y of V G fixed points is a weak equivalence in the non-equivalent sense for strong level equivalences, or a Serre fibration in the case of strong level fibrations. So how do you pass between these two characterizations? Well, one direction is clear. Here it's just a special case where the representation V is R to the M, and we have the tautological action of some closed subgroup of OM. And the other direction, we're exploiting that such a representation is up to isomorphism, really a continuous homomorphism from G into the orthogonal group. Now this homomorphism need not be injective, the representation doesn't have to be faithful, but the fixed points of G under X correspond exactly to the fixed points of the image of this representation homomorphism, which is then a closed subgroup of the orthogonal group. With these definitions at hand, I can already state the strong level model structure, so this formulated as a proposition, the strong level fibrations and strong level equivalences are part of a cofibrantly generated and topological model structure on the category of orthogonal spectra. And this I call the strong level model structure. The strong level model structure I consider as a fairly routine process. I don't want to go through it in details, and I'll just give you a reference. The next step is to get a better grip on the cofibrations. Step B, the flat cofibrations. In every model category, the weak equivalences and the fibrations together already determine the class of cofibrations, because the cofibrations are precisely the morphisms that have the left lifting property against acyclic fibrations, the ones which are both fibrations and weak equivalences. However, it's very useful to have a better and more explicit description of what the cofibrations look like. I need to warn you that in none of the examples that I discussed above are the cofibrations just the level-wise cofibrations. In all the cases, there is a condition that a certain stuff called the latching object, which assembles all the data from smaller dimensions, that this has to embed in a nice way into a particular level of the kind of spectrum that you're considering. These are called the latching objects, latching spaces, and latching morphisms, and I will now explain what these are in the special case of orthogonal spectra. I will give you 3 equivalent ways to look at the latching objects. The first one is in terms of the skeleton filtration. The skeleton filtration is a way of writing an arbitrary orthogonal spectrum as a sequential colimit of other orthogonal spectra that I'll call the skeleton. And it arises from the fact that the indexing category, which are finite dimensional inner product spaces, is filtered by the dimension of the inner product spaces. So the skeleton filtration is a natural way to write any orthogonal spectrum as a colimit of a sequence of other orthogonal spectra, starting with just a point. This will be the -1 skeleton of X, mapping to the 0 skeleton of X. This will just be the suspension spectrum of the 0th space, and then it will be more complicated, the 1 skeleton, and so on, and then the M skeleton of X. Moreover, there's a coherent way of understanding how you get from one step in this skeleton filtration to the next step. You should be aware, though, that the maps in the skeleton filtration, how you get from one skeleton to the next, and also the maps from a fixed skeleton to X are not in general injective maps. So the word filtration has to be taken with a grain of salt. It's a natural sequence, but not necessarily by injective maps. If, however, the orthogonal spectrum X is cofibrant in either the strong level or the stable model structure, and I will soon call these objects flat orthogonal spectra, so if X is cofibrant, then all these morphisms from one skeleton to the next skeleton are level-wise closed embeddings, and so are the maps from a fixed skeleton to X. So then it's really a filtration in the way you would think about it. How is this skeleton filtration constructed? We consider a topological category, O less than equal to M. So let this be the full topological subcategory. Of O, so this is the indexing category for orthogonal spectra, with objects, those inner product spaces, those V such a dimension is at most N. And then we can look at a truncated version of orthogonal spectra. Spectra less than equal to M. Here the category of based continuous functors from O less than equal M to based spaces. So, without this dimension restriction, if we took the full category O, this would be orthogonal spectra. Now we're just looking at a subcategory, functors on a subcategory, so you can think of these as kind of M-truncated orthogonal spectra. Orthogonal spectra where you only have the values at small dimensional inner product spaces. Then we can, of course, restrict. So a restriction functor from orthogonal spectra to orthogonal spectra truncated at M has a left adjoint. Then I write Lm goes from M truncated orthogonal spectra to orthogonal spectra. This functor also has a right adjoint, but we won't need this right adjoint. And the fact that these two adjoints exist is just a special case of general category theory or enriched category theory. These functors are enriched versions of left and right Carn extensions. As a left adjoint, it comes with an adjunction unit for an orthogonal spectrum X. The adjunction unit is a morphism of orthogonal spectra. We first restrict X to dimensions below M, so you forget a lot of information, and then you freely extend the values on the higher dimensional spaces, and this maps back naturally to X, and this I want to call IM, so this is a morphism of orthogonal spectra. And then the latching object is just a value of a particular such extension, so this I denote the M skeleton of X. So you can think of the M skeleton as the stuff in X that comes from inner product spaces of dimension at most M, and I repeat the warning that this morphism need not be injective in general. Now we can define the latching objects. The nth latching object, or latching space actually, of an orthogonal spectrum X is the based OM space so we take the skeleton in dimension M minus 1, and then we evaluate at the smallest example of an inner product space that wasn't in the indexing category here, so we evaluate at R to the M. And of course this is some orthogonal spectrum evaluated at R to the M, so this comes to us with a base point and with a continuous OM action. Moreover, if we evaluate this unit of the adjunction for M minus 1 at R to the M, we get a morphism of OM spectra, of OM spaces. And this is the latching morphism. For which I write mu M. And it goes from the latching space X. I guess I haven't introduced the notation yet, so this is LMX to X of R to the M. And this is the value of I M minus 1, so this is a junction unit, but for M minus 1 and at R to the M. Here are some facts about the skeleta, the latching spaces, and the latching morphisms. And all the facts that I'm going to list now are enriched category theory, and they're not topology or homotopy theory. First fact is that this morphism, co-unit of the adjunction, IM from the M skeleton of X to X is a homeomorphism, or an isomorphism of spaces at all inner product spaces of dimension less than or equal to n. This is just a special case of the fact that we're doing a left Kahn extension along a fully faithful enriched embedding, and such left Kahn extensions are really extensions. They don't change the values on that you already had. The consequences of this is that because the skeleton filtration stabilizes, at every inner product space V, X is the colimit of the skeleton filtration. So every inner product space V has some dimension, and as soon as you're in the skeleton filtration beyond the dimension of V, at V there's only isomorphisms coming, and colimits and limits in functor categories are calculated pointwise. So while the point where the sequence stabilizes varies, it always stabilizes, and so X is in a trivial way the colimit of its skeleton. Then you can wonder about examples, and important examples are the represented orthogonal spectra. The orthogonal spectrum OV blank, so functors out of a fixed inner product space. This is the one represented by V, has the following skeleton. So the M skeleton of the represented orthogonal spectrum? Well, it's either just a point if the skeleton dimension is less than the dimension of V, and it's everything O of V blank, or more precisely, the co-unit of the adjunction is an isomorphism if M is greater or equal to the dimension of V. So you can think of this as saying that the represented orthogonal spectrum is purely m-dimensional, so there's nothing happening in the skeleton filtration. Then you have everything, and then again, there's nothing happening. Another very useful fact is that you can use the skeleton filtration and the latching maps to say how you got from one step to the next, and thereby you get kind of an inductive description of the structure of an arbitrary orthogonal spectrum. The following commutative square of orthogonal spectra is a push-out. So suppose you already understand the m-1 skeleton, and you want to understand the m skeleton, then there's a very precise way in which you get from here to here by attaching something along the latching map. So here we're taking the represented orthogonal spectrum by OM. We use the fact that OM acts by precomposition with the latching space, which comes with the left OM action. Here we go via represented orthogonal spectrum blank smash over OM with a latching map that are called nu M. This gets us to the represented orthogonal spectrum smash over OM with a value of x at Rm. So then there's a morphism down here, which is adjoint to the identity. So after all, the latching object was defined at the value of this orthogonal spectrum at R to the M. So the identity has an adjoint, which goes in this direction, and here too. At Rm, the M skeleton is the same as x. So this is adjoint to the identity of x to R to the M, and this is always a push-out. So incidentally, this gives us a criterion for when this skeleton inclusion or this skeleton morphism is actually an inclusion, is injective, and you'll see that we want to know that the morphism, the latching morphism from the latching object into x to the R to the M is in particular injective, and then we get this is injective, and maybe this is even nicer like an equivalent cofibration. And then we have the same kind of nice inclusion condition for the respective skeleton. The next proposition explains why we care about latching morphisms. A morphism of orthogonal spectra f from x to y it's a cofibration in the strong level model structure. If and only if for all m greater or equal to 0, a relative version of the latching map, the OM map, from x of R to the M, glued along lnx using the latching map of x to glue here, and glued with lny using lm applied to the morphism f to glue this here, to y of Rm, and the map from here to here is f evaluated at Rm on this factor, and the latching map for y on the other factor. So this map is a map of based OM space. It needs to be an OM cofibration. Here's an OM cofibration. So what's an OM cofibration? So this is a cofibration in the projective model structure on based OM spaces, in the ones where fibrations and weak equivalences are tested by fixed points of all closed subgroups. These OM cofibrations you get by attaching orbits OM modulo a closed subgroup product with the inclusion of a sphere into a disk, and you keep attaching those via the small object argument. So this is the promised characterization of the cofibrations in the strong level model structure, and this will also be the cofibrations in the global stable model structure because we obtain it by a Bousfield localization procedure. I want to call these morphisms the flat cofibrations, and an orthogonal spectrum is flat. Well, if the morphism from the trivial spectrum to it is a flat cofibration, and if we expand the definitions, this means that if its latching map mu my from lmy to y of Rm is an OM cofibration for all m. Let me put this into context by comparing it to two of the non-equivalent stable model structures that have been constructed on the category of orthogonal spectra. The cofibrations that I call the flat cofibrations, which are the cofibrations in the strong level model structure, they coincide with the cofibrations in what Martin Stolz calls the convenient model structure in his thesis. And this is the orthogonal version of what Hovey, Shipley, and Smith call the S model structure in their paper. There are more flat cofibrations here, than there are in the projective model structure that is used by Mandel, May, and Schwede-Shipley. So there's also, this is historically the first stable model structure on the category of orthogonal spectra. The cofibrations used by Mandel, May, Schwede, and Shipley are also morphisms where this latching map is an OM cofibration, but there's the additional requirement that on top of this being an OM cofibration, the OM action on the target has to be free away from the image. So for every point in y of r to the m that's not in the image, the stabilizer group has to be trivial. I would like to give you two other perspectives on what the latching spaces are, and I leave it up to your own judgment to decide which ones you find more helpful. The first additional perspective that I would like to explain comes from an explicit presentation of what a left Kahn extension looks like. After all, Kahn extensions, if you evaluate them at some object, there's the pointwise formula for this, which is a co-limit for left Kahn extensions or a limit for right Kahn extensions over a suitable slice category. There is an enriched version of this, and if you spell this all out in the case of the indexing category for orthogonal spectra, you arrive at the following presentation for the latching space. So the latching space lm of x is a coequalizer in the following diagram. So here we're taking a wedge over all 0 less than equal to a less than equal to b, strictly less than m, or less than equal to m minus 1. We take the morphism space in the indexing category of morphisms from a r to the b to r to the m, smash morphisms in r to the a to r to the b, smash the value of x at r to the a. Then there are two continuous maps from this big wedge to another wedge, the wedge from 0 less than equal to k less than equal to m minus 1. And here we take the space of morphisms in the indexing category from r to the k to r to the m, and we smash this with the value of x at r to the k. This has a map to the nth latching object, which basically comes from the structure of the orthogonal spectrum, plus the fact that this k is strictly less than m, so it will actually land naturally in the latching object. There are two continuous maps from this big wedge to this big wedge. One of them comes by using composition in the indexing category to pull these two together, and the other map comes from this functor structure by letting this act on the r, so we're putting these two things together. And the nth latching space is a co-equalizer of these two continuous maps. There's a third perspective on the latching space that I would like to offer. For this one, you have to know what the smash product of orthogonal spectra is. So this is something I'm not discussing in this class, but I've discussed it in the previous two classes and the previous terms. And here's how this description goes. We look at the truncated sphere spectrum, which is the orthogonal subspectrum of the sphere spectrum, which is almost everywhere the same as the sphere spectrum. The only difference is that the value of this truncated spectrum at the zero vector space is just the base point. And for the sphere spectrum, we would have 2 points. We have the base point and the point 0. The structure as an orthogonal spectrum is as a subspectrum of the sphere spectrum. Now we can take this truncated sphere spectrum, smash it with the orthogonal spectrum X, and evaluate at Rm. This gives you a based Om space. And the exercise is to construct a natural isomorphism from this based Om space to the mth latching space. Now we're done with the strong level model structure. But this is, after all, only an auxiliary gadget. We're not really interested in this strong level homotopy theory in its own right. What we really care about is a certain localization, a Bousfield localization of this, namely where the equivalences are the global equivalences. So we already know what equivalences we want to have, the global equivalences, and it's part of the game that you have to make an intelligent guess as to what the local objects would be. For example, if we looked at orthogonal spectra with respect to the non-equivariant pi star isomorphisms, then the local objects would be the traditional omega spectra. Now we have a refined notion of equivalence, so we must have a more restricted notion of omega spectrum. And here's the kind of omega spectrum that we want to consider. An orthogonal spectrum X is a global omega spectrum if the following condition holds. If for every compact Lie group G, every G representation V and every faithful G representation W the adjoint structure map for which I write sigma VW, which was my notation for the structure map, and then a tilde to denote the adjoint. So this is the map which goes from the value of X at W to the space of based maps from the sphere of V into the value of X at V plus W. And on this space, the group G acts by conjugation, and this is a G-weak equivalence. Which, as before, means that for every closed subgroup of G, on fixed points, this map induces a non-equivariant weak equivalence. This is a very important definition, and I would like to offer some comments on this definition. So the first comment is that every global omega spectrum is in particular a non-equivariant omega spectrum. After all, if the group G is trivial, then every representation of G, including the zero representation, is faithful. So there's no faithfulness condition, and this is just saying that for all inner product spaces, the adjoint structure map is a non-equivariant weak equivalence. That's exactly what an orthogonal omega spectrum is. The next comment is that if G is non-trivial, the underlying G spectrum so in other words, when we give it the trivial G action of a global omega spectrum, is in general not an omega G spectrum. Not a G omega spectrum. Why is this? Well, a G omega spectrum would be defined by essentially the same condition, but without the faithfulness requirement. So a G omega spectrum would have the adjoint structure map being a G weak equivalence for all G representations V and W, not for the faithful ones. So this does not typically happen. On the other hand, because the faithful G representations are co-final in the poset of all G representations, in practice this is often not really a problem, and for most practical purposes these faithful G omega spectra behave very similarly to full G omega spectra. The next comment that I would like to make, that a global omega spectrum, that this is a very rigid kind of structure and it encodes compatible families of equivariant infinite loop spaces. So very roughly, what this condition is saying, that if you start at a faithful representation, and then if you go further and loop by the relative difference, you get a G space which doesn't change anymore. So in particular, you could extract this G space, but by evaluating X at your favorite G representation W, and then also looping by the sphere of W. And the G homotopy type of this G space would be independent of the choice of faithful representation, and it would be deloopable in the direction of every other G representation. So this is what I mean by a genuine equivariant infinite loop space. And moreover, you would have this structure for every compact Lie group. And the fact that they all arise from a single orthogonal spectrum has all sorts of compatibilities implicitly built into the theorem. I don't want to go more into detail, but just give you a reference where I'm more precise about this. The final comment is that because a global omega spectrum is such a rigid and such a strong structure, you don't find them very often in nature. It is extremely rare that something you can write down in closed form actually has this strong condition as a global omega spectrum. On the other hand, global omega spectra exist in abundance because a consequence of the global stable model structure is precisely that every orthogonal spectrum admits a global equivalence to a global omega spectrum. So up to this very fine notion of global equivalence, it is actually no condition to be a global omega spectrum. We can always replace an orthogonal spectrum up to global equivalence by a global omega spectrum. We would like the global omega spectra to be the fibrant objects in the global stable model structure. And then the standard procedure would require us to characterize them as the local objects with respect to a suitable class of morphisms. This is not so difficult to do, and here is how it goes. So let G be a compact Lie group as above. V and W G representations. And then we can represent the G fixed points of this functor as a functor of the orthogonal spectrum and the G fixed points of this functor as follows. So on the one hand, the orthogonal spectrum, where we take the orthogonal spectrum represented by W and then we divide out the G action on the source. So this represents the functor ascending X to the value of X at W, and then taking G fixed points. On the other hand, the orthogonal spectrum where we take morphisms out of V direct sum W, and then we smash over the action of G with the one-point compactification of V using the left G action, the right G action on here coming from the left action on V and the action of G on the sphere. And this represents the functor sending X to based G maps from SE into X of V plus W. And also the G fixed points of this particular map are represented by a morphism. So the map sigma tilde VW up here, and then taking G fixed points is represented by a morphism that I call lambda sub g, comma v, comma w, and it goes in the other direction, so it goes from O of v plus w blank smashed over g with sv to O of w blank modulo g. And what is this morphism? Well, this is kind of a represented spectrum and then taking orbits. So to define this, I just have to give you a special map. So this is adjoint to the G map from SV to O of W V plus W mod G. So that's the value of this orthogonal spectrum at V plus W. And then because we're taking over G, I have to give you a G equivalent map. And the map I'm taking is I'm sending V to the orbit of the pair consisting of the vector little v, comma 0 and the linear isometric embedding I, and then the G orbits. And I is just a direct sum embedding from V to V, from W to V plus W is the embedding of the second summit. So wonderful. We have found a morphism that represents the two sides of what determines global omega spectra. So we would like to add this morphism to the set of the generating acyclic cofibrations. Well, the first issue is that this morphism is not a cofibration, but fortunately source and target are cofibrant in the strong level model structure, or flat, as I just called them. So source and target of this lambda morphism are cofibrant. The morphism is not a cofibration, but we can then easily turn it into one by performing the mapping cylinder construction. So the mapping cylinder inclusion then we write C, G, V, W for this. So this is the morphism from the source of this, from O of V plus W blank smash over G with SV into the mapping cylinder. And the mapping cylinder is the interval 0, 1 plus smashed over this O of V plus W blank smashed over G with SV. So we're taking level-wise in the orthogonal spectrum direction the path space, but in the pointed version. And this is union with the target, with O of W blank G. And the union is formed along the map lambda G V W using the end of the interval, the 1. And this morphism C is using the beginning of the interval, the 0. So this mapping cylinder construction, like any mapping cylinder, deformation retracts onto its target. So this is even up to homotopy equivalence, and in particular up to global equivalence, just a fattened up version of this. But the advantage now is that the C morphism is a cofibration, a flat cofibration, which the one previously wasn't. All right, and now we're in the situation to define the standard way of generating acyclic cofibrations. So here's the definition. Let K be the set of morphisms of orthogonal spectra of the following form. I take C, G, V, W, and then box product with the inclusion of the boundary of a disk into the disk. So this means I take the source smashed with dn plus union with the target smashed with boundary dn plus over the source smashed with boundary dn plus, and then mapping to the target smashed with dn plus. This is the box product construction, the monoidal product if you have morphism of orthogonal spectra and a map of spaces. And I take these, the set of all these, running over n, g, and now I'm just going to say in words what we let this run over. So first of all, we let this run over n greater or equal to 0. For n equals 0, this is actually empty, and I guess I wanted to add disjoint base points because we're always in the base situation. So for n equals 0, this is just a point. And then I let it run. I would like to let it run over all GVW, as in the definition here, compact Lie groups, arbitrary G representation V, faithful G representation W, but of course this would be too many, that would be a class, but we just take a set of representatives of the isomorphism classes of such triples. So representatives of the isomorphism classes of triples GVW, where G is a compact Lie group, V is an arbitrary G representation, and W is a faithful G representation. So these maps, because the source and the target of the lambda maps are flat cofibrations, these CGV maps will be flat cofibrations, and then the box product, because the strong level model structure is topological, this again will all be cofibrations. And on the next whiteboard, I'll tell you that these morphisms now detect the locality condition, they detect the global omega spectrum property. A special case of a fairly general fact is the following proposition. An orthogonal spectrum X is a global omega spectrum if and only if it has the right lifting property with respect to the set of flat cofibrations K. So I explained a little bit earlier that these are all flat cofibrations. The proof of this fact is playing around with the representability property of the morphisms that made up the C's, source and target of C in the first place, and of the fact that these inclusions of spheres into disk detect whether a map of topological spaces is simultaneously weak equivalence and a Serre vibration. And here's a reference for the general fact of which this is a special case. So this completes the third step that I call step C in the general procedure to establish such stable model structures. The next step is a reality step, and this is the one which is much less formal than the other ones. Step D would be that all morphisms in the class in the set K are global equivalences. After all, if we want the global omega spectra to come out as the fibrant objects, then the equivalences can be detected as those morphisms that in the homotopy category induce bijections into all global omega spectra. And by design, or by this proposition rather, all the morphisms in this class will have this property, that if you map them into a global omega spectrum in this strong level model structure, you will get bijections. So for this to actually work out, this is a reality check that needs to hold, and this is where some truly global mathematical thing is actually happening. This is something which is not formal or just a special case of general nonsense. Okay, so it suffices to show that the morphisms lambda, G, V, W, and let me remind you where they started and where they ended, O, V, W, smash over G as V to O of W modulo G, that these are global equivalences. And the key condition is that whenever G acts faithfully on W. So why is it enough to show that? Well, first of all, from the lambda morphism, we got to the morphisms that are denoted by C, G, V, W by a mapping cylinder construction. But the target of the mapping cylinder is even homotopy equivalent to this, in particular globally equivalent. So whether this map is a global equivalence, that's equivalent to the mapping cylinder inclusion being a global equivalence. And then the strong level model structure is topological, so box product with the inclusion, with some cofibration, in particular the inclusion of a sphere into it. This doesn't change the question of whether a morphism is the global equivalence or not. So the real mathematical issue is showing that these particular morphisms are global equivalences. And now this is an analog. And you remind you of something we have discussed earlier. So this is really a stable version of what would unstably be the morphism of orthogonal spaces represented by V plus W modulo G, and then the restriction morphism to the morphism of orthogonal spaces just to the orthogonal space just represented by W modulo G. You know, the difference between the linear isometries category and the indexing category for orthogonal spectra is that we also have a vector in the orthogonal complement. And so if we enlarge the source, the orthogonal complement becomes smaller, and this extra sphere is sort of compensating for the fact. So whatever you unstably just have a map out of something, stably something additional here has to be cancelled by a sphere, very roughly speaking. And the analog, something that we showed in lecture number 5, is that this is a global equivalence of orthogonal spaces unstably. So I cannot formally deduce this stable statement from this unstable statement, but I think we should think of it as a stable analog. And now this is the key mathematical step, so let's try to prove this. So let me first formulate it as a theorem. For every compact Lie group G, every G representation V, and every faithful G representation W, the morphism lambda G V W, this one here is a global equivalence of orthogonal spectra. Here is a reference for this theorem in the global homotopy theory book. In it, of course, you can find a proof, but I would like to give a different and alternative proof. This is, after all, a very important result in the theory, and it doesn't hurt to have two proofs. The proof in the book is really verifying that the morphism induces an isomorphism on G equivalent stable on K equivalent stable homotopy groups for every compact Lie group K. But of course we can also characterize equivalent equivalences by looking at the geometric fixed point homotopy groups as opposed to the genuine homotopy groups, and that's what we're going to do here. So this is a different proof of the same result. So we check that lambda G V W induces isomorphisms on the K geometric fixed point homotopy groups for all compact Lie groups K. And as a few times before, I would like to give you the essential ingredients and the essential ideas of the proof, but I will not completely to 100% formalize all the details here. I will use a certain reformulation of the geometric fixed point homotopy groups as the non-equivalent homotopy groups of a certain spectrum. So here's how this goes, and for this we let X be any orthogonal spectrum. Could even be an orthogonal K spectrum, but that's the generality which we need. So in all the definitions of geometric fixed points and genuine homotopy groups, the complete K universe will pop up. And the complete K universe, of course, has a fixed part, which is isometrically isomorphic to R infinity, and it has the non-fixed part. So let us choose an isomorphism to the orthogonal direct sum of R infinity with the understanding that the group K acts trivially here, and then what I call UK perp. And UK perp is just the orthogonal complement of the fixed part, UK orthogonal complement UK fixed. So in other words, this is infinitely many copies of the trivial G representation, and this is infinitely many copies of every other irreducible non-trivial representation. So then, let me just give you this formula in dimension 0. The other integer dimensions are essentially the same. So what were the geometric fixed point homotopy groups? Well, this is the co-limit over finite dimensional sub-representations of the complete K universe. And then, in the geometric fixed point homotopy groups, we have to take non-equivariant based continuous maps and homotopy classes of such from the K fixed points in this sphere into the value of the orthogonal spectrum at U, and then K fixed points. And then these are non-equivariant spaces, and we'll take based homotopy classes of non-equivariant maps. Now, using this decomposition into a standard R infinity and the free part, we can write this as a co-limit in 2 steps. This is a co-limit for n greater or equal to 0. We're going to exhaust the R infinity by the R to the n's in the standard way. And then there's a second co-limit for U prime in finite dimensional sub-representations only of the fixed point free part of the complete universe. And then we're going to take S to the n, because the other summand has no fixed points. All the fixed points lie in the first one. And then we evaluate x at Rn plus U prime. And then we take K fixed points in here. So the isomorphism between these two descriptions is again a cofinality argument. Instead of running over the 2 colimits, we can run over a diagonal colimit. And now, if we look at this carefully, in the colimit over representations that don't have any non-zero fixed points, the structure maps passing to fixed points don't increase the dimension or anything. So we can take the colimit inside as long as we have a closed orthogonal spectrum. So this is one of the things where I'm not completely precise. Here I want that all the structure maps are suitably closed embeddings, which will be the case for the orthogonal spectra that we are going to consider later. So then I can put one of the colimits inside by compactness. This is the colimit over n greater or equal to 0, maps from Sn into x of Rn plus, and now we take the complete K universe, but only the fixed point free part, and based equivariant maps. And now the thing in here is visibly a spectrum, because now we can just let the n vary, and if we replace the n by some coordinate free in a product space, we could even make it an orthogonal spectrum. So these are the non-equivariant homotopy groups of a certain orthogonal spectrum that consists of the spaces x at Rn, direct sum UK perp, and then K fixed points. And I just see that I've forgotten the K fixed points here. So I will continue to work with this description. In general, the K geometric fixed points of an orthogonal spectrum, I have rewritten them as the non-equivariant fixed points of a certain spectrum, which could even be made an orthogonal spectrum whose nth term is this non-equivariant space. I want to show that the morphisms lambda, G, V, W are global equivalences by checking that they induce isomorphisms on K geometric fixed point homotopy groups for all K. I'm going to use the description we just established of the geometric fixed point homotopy groups as a non-equivariant homotopy groups of some other spectrum whose nth term is this non-equivariant space. So let's work out this description in the case of the source of the lambda morphism. So let's look at it. Let me restrict to dimension 0 again. The other dimensions are essentially similar. Of O of V plus W blank smash over G with SV. So I'm going to expand this definition. It's going to be pi star of the orthogonal spectrum whose nth term is the following. It's O of V plus W evaluated at Rn direct sum UK perp smashed over G with SV, and then the whole thing taking fixed point outside, and this runs for n greater or equal to 0. Now I'm using the based version of some fact that I've already used in lecture 6, and I had given you a reference at that point. After all, we're in the situation here that the group G acts faithfully on W and hence also on V direct sum W. So the action of G on this space by precomposition is free, at least away from the base point. Of course, there's this base point at infinity, which is fixed, but no other point in this is fixed. And there is a based version of this proposition that I stated in lecture 6, which said that you have a commuting G action and a K action. The G action is free, that by taking G orbits and then K fixed points, there was a formula for this. And here's the based version. In this special case, we need OV plus W into Rn direct sum UK perp, smash over G with SV, and then taking K fixed points. So the formula is now a wedge because we're in the base situation. It was a direct sum disjoint union in the unbased situation. This is over conjugacy classes of continuous homomorphisms from K to G. And then we had to take the fixed points under the graph inside. So this will be O of V plus W into Rn direct sum UK perp smash SV. We have to take fixed points under the graph of this continuous homomorphism. So we choose one representative in each conjugacy class. And then the centralizer of the image, which I denoted by C alpha, will still act on the gamma of alpha fixed points, and we have to divide out that. So in our situation, we can simplify this summand a little bit further. So this is a wedge over all alpha from K to G. Now the graph has two components, the G and the K. The G acts here, the K acts here. So this is the same as taking, first restricting the representations V and W along this continuous homomorphisms, and then taking morphisms into Rn plus UK perp, which is a K action, taking K fixed points of the whole thing. This is the gamma of alpha fixed points of that part. And here we just have S of alpha upper star of V. We restrict the action from G to K along alpha, and then we take K fixed points of this. So that's what the gamma alpha fixed points of this smash product are, and then the whole thing still divided out by the centralizer of the image of alpha, which is a closed subgroup of G. Now we can rewrite this a little bit further. So this is a wedge over all conjugacy classes of continuous homomorphisms. Now, when is a point in this space fixed? So by definition, points in this space, well, there's the point at infinity, which is fixed, and all other ones are pairs consisting of a linear isometric embedding from this inner product space to this infinite dimensional inner product space, and a vector in the orthogonal complement of the image. Now, such a pair consisting of a linear isometric embedding and a vector in the complement is fixed if and only if, first of all, the linear isometric embedding has to be K equivariant, and also the vector has to be K fixed in itself. Now, this is some K representation where this is the trivial part and this is the part without K fixed points, and this is some other K representation which also decomposes into a fixed part and its orthogonal complement, which is the part without fixed points. And K equivalent linear isometric embeddings have to preserve the isotypical direct sum embeddings. In particular, they have to take fixed vectors to fixed vectors, and they have to take elements in the orthogonal complement of the fixed part to elements in the orthogonal complement of the fixed part. So that means that this space decomposes, first of all, as another space in the indexing category for orthogonal spectra, but there I take alpha upper star of V direct sum alpha upper star of W, K fixed points here, K fixed points here. And of course, the K equivariant map has to send this into the K fixed points here, which is only the R to the N. And since these are all K fixed, the vector in the orthogonal complement can be arbitrary because all vectors in the orthogonal complement are fixed because the action is trivial. And then there's the other thing, the linear isometric embedding in the base space also sends the complement of the fixed points to the complement of the fixed points. So we also get a linear isometric embedding from alpha upper star of V perp, by which I mean the orthogonal complement of the fixed points in alpha upper star V plus alpha upper star of W perp into the fixed point free part, which is this part, U of K perp, and this has to be a K equivalent map with a disjoint base point. And over this, we only have points in the base and the zero section, because we're exactly mapping into something where only 0 is the only K fixed vector. So the vector that is in the orthogonal complement, if it's not the base point at infinity, has to be the 0 vector, which is why we really have only linear isometric embeddings embedded as the 0 section on this orthogonal complement bundle. And then we still have S of alpha upper star of the K fixed point, so this hasn't changed. And the whole thing modulo centralizer of the image. So this is the description that I want to work with, and I just want to abbreviate this a little bit. So let me write X alpha for the spectrum which has these terms. So the spectrum consisting of O alpha upper star V K fixed, alpha upper star W K fixed, direct sum, into a varying variable, which will be in Rn, smash K equivalent linear isometric embeddings from alpha upper star V perp, direct sum alpha upper star W perp into U K perp with a disjoint base point, smash S alpha upper star V K fixed points. The whole thing divided out by the action of the centralizer of the image. And now we let the n run, and this is now a spectrum where we let the Rn in this variable run. And then I can summarize this whole discussion by saying that the K geometric fixed point homotopy groups of the orthogonal spectrum O, V plus W blank smash over G with SV are isomorphic to a direct sum over conjugacy classes of continuous homomorphisms from K to G. And here I'm exploiting that the spectrum of which we're taking non-equivalent homotopy groups decomposes as a wedge indexed over these conjugacy classes, and non-equivalent homotopy groups take wedges to direct sums. And then it's the non-equivalent homotopy groups of Fx alpha, where X alpha was this non-equivalent spectrum. And this maps to the direct sum indexed by the same conjugacy classes of continuous homomorphisms, pi star of X prime alpha, where the X prime alphas are exactly the same construction, but with the representation V being the trivial representation. Because when V is the trivial representation, this goes away and this becomes the target of the lambda map. So this is the K geometric fixed points of the target of the lambda map, O W blank modulo G. And the morphism lambda respects this decomposition into wedge summits, and so it respects this decomposition into a direct sum, and hence it's enough to show that we get a non-equivalent stable equivalence on X alpha to X prime alpha for every alpha. I have reduced the claim that the morphisms lambda G, V, W are global equivalences to a bunch of non-equivalent stable homotopy statements. Namely, for every continuous homomorphism from a compact Lie group K to the given compact Lie group G, I have defined two non-equivalent spectra, which I call X alpha and X prime alpha. X prime alpha is really a special case of X alpha, namely just where the representation V is set to be 0. And here are again what the nth terms of these non-equivalent spectra are. It's a relatively complicated definition. The map down is on this factor. It's the restriction of a linear isometric embedding to the second summand. And it takes these two things together also by an evaluation morphism, where this S alpha star V is cancelling this alpha upper star V K. Now I have to show that this morphism of non-equivalent spectra is a non-equivalent pi star isomorphisms, and the proof consists of two observations, which I'm not completely formalizing. The first observation is that the morphism before taking orbits is a pi star isomorphism, non-equivalent, So in fact, both of these things are really orthogonal spectra with an action of C of alpha, and all the maps come from a C alpha equivariant morphisms. I'm not going to consider them as C of alpha orthogonal spectra in the genuine sense. I'm considering them as orthogonal spectra sort of with a naive homotopy relation of an action. So before I divide out the action of the centralizers, I'm in the situation that this space here is actually weakly contractible, because this is the fixed point free analog of a complete universe. It's a complete fixed point free universe, and this is a finite dimensional fixed point free K equivalent representation. Such spaces of embeddings are contractible, and the same is that this space is contractible. So even level-wise, this factor isn't seen, it doesn't make a difference. And on the other hand, this sphere of alpha upper star vk fixed points is cancelling this thing here. If you remember from the lecture a year ago on non-equivariant orthogonal spectra, putting some inner product space in the O variable is a desuspension. And this desuspension by alpha upper star vk is cancelled by this. So this is an example of the non-equivariant lambda morphisms that are non-equivariant equivalences. So that was the justification that before passing two orbits of the centralizer of the image of alpha, we have a non-equivariant equivalences. And then the other observation is the C of alpha action is free away from the base point. Free away from the base point. And nice enough. And here I don't want to be precise. You know, dividing out a free action tries to be a homotopy invariant construction. It's not even unstably, in the base context, probably a homotopy invariant construction in complete generality. If you have a weak equivalence between equivariant spaces where the action is free away from the base point, then you need some non-degeneracy hypothesis on the base point. You're always safe if you assume equivariant CW structures, and there is a stable analog of this. If you have a compact Lie group acting on orthogonal spectra, the action is free in every degree, in every level, and the level-wise things are nice enough, then you can divide out this free action, and a non-equivariant equivalence, which is also equivariant for the action, is a non-equivariant equivalence on the strict orbit. So I'm putting these two things together. This shows that the x alpha to x prime alpha is a non-equivariant pi star isomorphism, hence the direct sum, the wedge of all these is a pi star isomorphism, hence this is, and hence lambda g vw is a global equivalence. So this is the end of the proof. This was the main mathematical work we had to do, and the main thing where something's actually happening. There's one fifth step in the standard procedure, that was the step E. And this is Bousfield localization via the small object argument. And this is again a routine step. I don't want to say very much about it. So maybe just what kind of class of morphisms do you perform the small object argument with respect to? So the one where you want to produce a fibrant object, you're going to use the acyclic cofibrations, the generating acyclic cofibrations that you already had in this strong level model structure. I didn't make it explicit, but that's also reasonably routine. And to this, you're going to add these morphisms K that were detecting the global omega spectra. These are also flat cofibrations and stable equivalences, so they're also in the class that you want to be the acyclic cofibrations. So the generators for the strong level structure plus morphisms K, and then you do the small object argument with respect to this class, and that produces fibrant replacements, and then you have to do everything in a relative version. You don't just want to fibrantly replace an object, you want to make a factorization, but these are all routine steps, and in the end you get the following main theorem for today, and in fact one of the main results in the foundations and the underlying theory of this, and this is the global model structure, global stable model structure. And let me summarize it as follows. The global equivalences and flat cofibrations. So in other words, the cofibrations in the strong level model structure that we discussed in detail a little bit earlier are part of a stable topological, cofibrantly generated proper model structure on the category of orthogonal spectra. So by giving you what the equivalences are, the global equivalences, and what the cofibrations are, I have implicitly also pinned down what the fibrations must be. These are the global fibrations, as I call them. There is a more explicit characterization of what the global fibrations are. You can find it here. And it's basically a relative version of what a global omega spectrum would be. It's a relativized version of that. So this is a key result. This is the last thing I wanted to explain in today's lecture. In the next lecture, I will talk about the global stable homotopy category in some more detail, and I will in particular talk about the triangulated structure, and I will prove to you that it's compactly generated, and there I will use the global model structure in the proof. This is all for today. Thank you for your attention.